Okay, so we start for a more formal construction and proceed along the line which will take us beyond this morning's. This is the last hour in the morning session. So it is the propagator as a transition amplitude. Propagator as a transition amplitude. Let's play with this intensively. What was the expression we had? xt, x0, t0. Now I go to the more orthodox notation of using the same labels for the x's and t's. This was x e to the minus I over h bar h t minus t0 x0. Remember, this was the formal expression that we have started with, and then we have inserted energy or momentum, again, completeness relations associated with the energy and momentum for the free particle to get that particular expression for the free particle. Remember that it is a determinantal d factor times an e to the I over h bar s was achieved for a free particle. So we should keep it, it's very specific nature of that explicit expression. Now this is the general form of the quantum mechanical expression. We can do many things with this. First of all, notice that this is nothing but, by the way, if I consider now, before proceeding, consider the following quantity. Consider a set t0 equals 0 and set x equals x0 k x t and x0, which is x and x e to the minus I over h bar. This is sort of a side remark to give you a true feeling on the possible uses and implications of this new quantity, which is we have called the propagator or the K. Of course, it's a nice exercise mathematically and intellectually, but this exercise is meant to point out the possible usages of this. It's a side remark. What is this really? If I now consider the integral of this, consider the k x t and x0 integral e cube x x e to the minus I over h t and x. Let's try to understand the mathematical meaning of the right-hand side. When you are given an expression of this sort, there's an operator which you recognize as ut0, something time evolution operator, which is important. You sandwich it between x's and sum. Is this the trace of e to the minus I over ht? In the x basis. Traces are invariant under representation changes. Remember, we have proven that in general terms. So once it is identified as trace of the time evolution operator, a particular form is the trace in the x basis. I can write it in the p basis. I can write it in the energy basis, any basis I like. For example, then I can equivalently write it as ei e to the minus I over h bar ht ei. That's also a trace in the E basis now, energy eigenvectors basis, which becomes what? this expression. So trace of this expression is really that. Is there anyone among you who recognize this expression? What is it? Z, right? Partition function? If you, of course, do the proper transformation. If you replace it with 1 over beta. If the I times the Euclidean rotated time is identified with the inverse temperature, then you get the partition function. So anything you construct on this math, the formalism you develop in here will be directly applicable to the statistical mechanics, which is a very important theory, which is a very important field of research, right? From superconductivity to whatever. So you see the connection. This is the related to this partition function Z. So trace of K, the trace of the propagator, it also have other beautiful and very profound applications in different fields of mathematics. The Chern index or stuff like that, those topological invariants are also spin-offs of these. So it's a very important field which pays a lot to go through with some detail. I could have followed Sakurai's version. From this point on, I deviate from Sakurai. I didn't like it. Sakurai starts from Feynman's formula and plays with it and try to convince that it is a good identification of this transition amplitude. But I will really go through formal discussion because in the 70s, some of those important developments in the field of path integral came from my division, my group of research. So I think I can use that privilege to go through a little more detail in this, really. Okay, so this connection is important. Any one of you who would like to push it beyond, enjoy it yourself. And he also has another really not so aesthetically looking, by the way, there's a minus sign for the convergence. The transformation should be done in such a way that IT goes to 1 over beta. IT goes to beta. Identification is beta is just this. Euclidean transformation, beta is 1 over KT, right? If you want to, temperature and time is inversely proportional, and there is also Euclidean rotation. This is the exact transformation which takes you from Feynman's propagator in quantum mechanics or quantum field theory to the partition function in statistical mechanics. Remember, you can compute free energies, etc., by taking the partial derivative of the partition function with respect to beta, etc. There are beautiful consequences of this identification. There's also one more side remark concerning this. Let me also further. He calls this, gives this a name. That's the K itself. And this, after the integration, taking the trace, he calls this G. And that's fun. So I cannot resist the temptation to talk about that fun. What is the Laplace transform of this G? G is a function of t. Notice that here G is a function of t because we have identified the x. T is the free variable by choosing the origin of time as 0. This is just a function of t. He takes the following Laplace transform the following Laplace transform. dt divided by IH bar. This is for dimensional reasons, and integral is from 0 to infinity, not minus to plus, but 0 to infinity. gt, g is the trace of the k, remember, e to the I over h bar et. It didn't do anything. It is a Laplace transform, definition. You'll see the power of this, as is the case in here. The connection to the partition function, this time Laplace transform of it, will enable us to identify the energy spectrum directly. It's a neat formula. So if I substitute the GT written in the energy, as it's a trace is independent of the representation. I use the energy representation, this expression, k e to the I over h bar ekt. So what do I get? I get the following: sum k dt over ih bar e to the I over h bar e minus ek t integral 0 to infinity. When you start reading some beautiful papers connecting quantum field theory to topology, you see such formulas. And if you don't know the background, how simple the background is, you may get aved, thinking as if there is something insurmountably profound behind it. All these things are really, you'll find its counterpart in those more sophisticated versions. So what is this expression for? Well, can I integrate this? In principle, you can carry out the t integration to get something. Let's try to integrate this over t and let's see what do we get. A naive integration will be, well, forget these numbers, dt. 0, this is the important, and that's the important thing that you have to keep an eye on. If you integrate this, what you get is the following: e to the I over h bar e minus ek t divided by I over h bar e minus ek. Integral 0 and infinity. 0 to infinity. Well, at the 0 version, at the bottom end of the integral, when you carry out, there is no problem because this factor is exponent being 0 gives you minus 1 divided by this. So 1 over e minus ek. But at the upper infinity, the problem is dangerous. Why it's dangerous? Because when t is infinite, t is here omega t, right? T is when it's infinite, it oscillates violently. So you don't know what result you get. Usually when in those infinite values of periods are dangerous things. You have to introduce a mathematical trick to tame that violent oscillations at infinity. What people do is add an I epsilon. Those of you who have seen scattering theory, perhaps you haven't seen it from me, I do it. It is a Lippmann-Schwinger equation. And there's Feynman-Schwinger trick, sort of. They add to tame that violent oscillation and to make this regularize this integral, because this integral is, at this point, it dangerously it oscillates dangerously. So you add an I plus I epsilon in there. And eventually take the epsilon goes to 0 at the end of the day. And take epsilon goes to 0 when you are finished. Here, of course, there will be an I epsilon in here. There will be I epsilon in the numerator and denominator. And what does the numerator one does? Let me check the numerator. Instead of writing everything from scratch, when you add e minus ek plus an I epsilon, I times I is minus, and so you have up there the following: minus epsilon over h bar plus I over h bar e minus ek times t times, of course, everything is t. When t goes to infinity, that's a dangerous point I am checking. Zero, at the zero part, there's no problem. When t goes to infinity, this is, epsilon is a positive real, I times epsilon we added. E times infinity with a minus sign in the front kills this entire thing, because you write this as you can write it in the following form, right? Comfortably. You factorize. And when you let now t goes to infinity, this oscillates violently again, but this immediately goes to zero, kills the entire thing. So the result becomes, this thing becomes sum over k times 1 over IH bar already was sitting in there, and another, the infinity now didn't contribute, minus 1 divided by I over H bar, E minus EK plus I epsilon. I will let epsilon goes to 0. Notice that this that cancels thanks to the extra minus we have in there, and the result becomes, so GE becomes sum over K 1 E minus EK. If you want, you can retain I epsilon as long as you need it, that you can drop it at the end. What is this expression? EK are all the possible energy values in the spectrum. And they appear as the poles of this G, Laplace transform of the trace of K. So trace of K, which is related to the partition function in one respect, is also have this new interpretation. When you take the Laplace transform of it, by looking at the poles of the Laplace transform, you have the energy spectrum. You construct this, and you look at the pole structure, and you write down the energy spectra. If you were smart enough, you were doing energy spectrum of the. If you're trying to study the energy spectrum of the hydrogen atom in this sense, you should be able to get that expression right from there as the poles. You would be getting it via Laplace transform. This is one way of attempting to solve the energy spectrum, but I warn you, this approach I don't like that much because it involves some input from already known part. And then you may ask, if I have the alternative formulation of the canonical formulation, I know the results, why to feed that in and get another version? It doesn't produce anything new. It doesn't yield anything new. Well, that criticism is right if you are adapting yourself to this line of reasoning. Well, this is not Feynman's. Now I turn my attention to the Feynman's. Go back to this expression again. Okay. Here is the propagator. So we say this is the transition amplitude because you act on it by this time evolution operator, you carry it to the t, and then you project on x, and so that is really how much of the original finds itself in x. So it's an overlap. So it's really it is really a transition probability. In that respect also, this is different than the canonical formulation. Canonical formulation is static because it is asking you, well, I don't want to mislead you, static in the following sense. It doesn't involve dynamical transitions. It asks you to find the probability at a given point, at a given time. But here it asks you to find the transition from a given initial point to a final one with the corresponding times. It's really dynamical. So it's more involved with the transitions rather than the static existence amplitudes. How do we proceed to construct this? Well, the construction proceeds along the following way. First of all, let us remind ourselves the Heisenberg picture description of the position operator eigenvalue problem. In the Heisenberg picture, if we start with the Schrödinger picture eigenvalue equation, knowing the natural consequences that these bases are orthonormal and they are complete, so they constitute a good basis, right? E cube x, x and x, I. So that is the Schrödinger picture basis as defined through this operator. Capital letter stands for the operator. How do I go to the, from Schrödinger to Heisenberg? I multiply this with I over h bar ht, right? Then what do I have? E to the I over h bar ht x e to the I over h bar ht and x. Right hand side is already done because that is the xt in the Heisenberg, x of t or xt. And what about here? I haven't, in order to be able to see it, I have to insert an identity in here, ht times the plus of it, inverse of it. Nice. This is indeed x and t in the Heisenberg, and this is the Heisenberg picture version of the h. Indeed, it's transformed properly. So what do I get? I get a new equation with the same eigenvalue originally as in the Schrödinger case, but new eigenvectors. What is this new spectrum? Notice that you say what else it could be? Eigenvalues stay the same. Why? Because eigenvalues are invariant under unitary transformations, and the transformation which takes you from the Schrödinger to Heisenberg is unitary, therefore it's natural that eigenvalues stay the same, and vectors differ. Question, are these new vectors also still complete and orthonormal? That's a good question. So if I have new basis now, xt, which I denote with the h in the Heisenberg, do I have the xt, x prime, t prime, h and h? Is it d cube x minus x prime? Or am I misleading you? What is the trick that I have done? You remember when we were discussing Heisenberg picture, we said algebra stays the same provided that you stick to the equal time. At equal time, x of t, x prime of t commute. But if you go to a different x at different time, they do not commute, they behave as different operators. So the orthonormalization, should it be at the same time or not? It should be at the same time, right? Because if you write this as a time evolution, this unitary operator times the Schrödinger operator, it involves e to the I over h bar h t prime. If it involves the t, that factor sticks out and you don't get normalization. So it is something we have to keep an eye. It is important. And what about this is the orthonormalization, what about the completeness? How do I write the completeness? xt, x h bar, d cube x, do I get the completeness as before? That is the question. The eigenvectors of the position operator in the Heisenberg picture, are they still complete as in the case of Schrödinger picture? Well, you say, of course. And you may say, what? Why, of course? Well, the proof is really cheap. Huh? You do the following. What is the completeness of the Schrödinger eigenvectors? It is this. You multiply this from left by I over h bar ht, and from right by e to the minus I over h bar ht. Can I? Of course. And right-hand side doesn't change because unitary times the inverse gives you 1. What about the left-hand side? Well, left-hand side gives you nothing but the transformed xth and xth is 1. You say, why this is minus and this is plus? Of course, this is the ket. It is acted upon by e to the I over h bar ht, and the bra is acted upon by the dagger of it, which is the minus. So indeed it's complete, fine, perfect. So when we go to this Heisenberg picture, we have the position operator eigenvector. Position operator eigenvector basis plays a crucial role in Feynman's derivation. Please keep an eye on it, that's important. So, but the nice properties that we had in the Schrödinger picture are retained and we can keep using them. Let's do that. Okay. So I'm interested, going back, that. What is that? Well, that's really, if I compactify the notation, it is this thing, right? It is this transition amplitude. If it is non-zero, what does it mean? It means that xt, that is Heisenberg picture eigenvector at t, and Heisenberg picture eigenvector at x0 are not orthogonal. And there is an overlap. That is quite different than x and x prime of Schrödinger picture. The overlap is delta function. But when there are two different points, x at t and x0 at t0, the states, associated states, are not orthogonal, and there is an overlap between them. And what we are finding in the form of a transition amplitude is the overlap between these two. So in simplistic terminology, transition amplitude is the overlap between the evolved and the original position operator eigenvector basis. Good. We can do the following. Let's keep this compact form and insert in between identities. You may wonder why we do so much insertion of identities. But let me plot a T-line picture, and then I will try to plot a space-time picture. That's really beautiful picture. So what is this? This is the T-line. I start with the x0, t0. That's the 0 points. And that's a 0 point. That's the t1. T2 with equal segments, and labels are T1, T2, etc. So that's the 1.1, 0.2. That is, X is labeled by 0, T is labeled by 0. Similarly, X is labeled blah blah. So you go along and you have a TK plus 1, and all the way to, the labeling is important in here, T, let me put up, let's make it aesthetical. K plus 1, Tn minus 1, this is the Tn. That's really my xt. My final point, I labeled it as n. First of all, the logic. There are equal segments. My initial time physically is t0, and final time is t. I label the initial time as 0 sticking to original 0, and the final one is n. How many intervals? There are n intervals. That's important. And how many subdividers? I call it sub because this initial and final one are fixed. Intermediate ones are not fixed. I will let the number go to infinity, and the intervals, the size of the length of the interval will go to 0. So the fixed 2 points are excluded, and there are n minus 1 subdividers. Well, when you are doing pulse integral, one of the most important things is to keep track on the labels and these subdivisions. Introducing discretization on time or space axes. And being someone who spent several years of my past life on it, I know how terrible it can get if you do any mistake in these countings. So what is the purpose of this insertions? I say my ultimate purpose is to go from, well, notice that it's in the opposite order. X0, T0. If we were using Arabic alphabet, there would be no inversion. You go in time axis from left to right, and in writing you go from right to left because you start from the X0, T0, come to XT. And you insert identities at each point. At that point, at these intermediate points, identity is what? Identities of the completeness of eigenvectors of the position operator. Let me insert one identity at the neighboring point of the final one at Tn inverse. So what is it? D cube x n minus 1 x n minus 1 Tn minus 1 x n minus 1 Tn minus 1. Well, unfortunately, I cannot write it in a smaller fashion, so I need a larger size blackboard, apparently, to depict everything, so it is symbolic. I put one insertion next to the last point in here, and there are infinite, well, so many subdividers, but it's going to be those points, and I will come next to here and put another identity, insert another identity in here. D cube x1, x, yeah, that's 1, right? Yeah, that's 1. T1, x1, T1. And all the others are to be inserted accordingly. For each point, I insert an identity. How many? 1 to Tn minus 1. So there are how many integrals? N minus 1 integrals. Important. N minus 1 subdividers, dividers, thus N minus 1 intermediate integrals, What did I achieve, really? Notice that if I use another color, look at that, the rightmost, the futuremost point. At the futuremost point, there is this transition. At the earliest most, that is to the left point, I have this transition. N to n minus 1, n minus 1 to n minus 2. So these identities, though these transitions are relating to neighboring points. So what I need to do is, I need to construct, if these are of infinitesimal lengths, need to construct the transition amplitude, because we said it's the transition amplitude t x k minus 1 t k minus 1 x k t k. Or perhaps, yeah, here is the other point is next to here. I take them to be generic ones. If I can find the transition of such an typical generic infinitesimal transition, then I will be able to multiply them all. Notice that the full single finite transition is the equivalent to the product of here n many transition. It's the composition law. That you can either directly go from the endpoint, from here to there, or you can go in as many steps as you like. And when you let the size of the intervals go to 0, you can go in infinitesimal sequential steps. You get the same result. Single transition or many transitions, in principle infinite. So this is the generic expression, which we have to construct and then put together everything. Let me finish that construction of that generic one. Then eventually I will put everything together, paying attention to these complicated cellular structure on time and space axes. What is it? This is an infinitesimal. Constructed transition, the infinitesimal. That's important. Generic infinitesimal transition amplitude involving what? Involving a tk minus tk minus 1 I define as epsilon, and this epsilon is equal to t minus t0 divided by n, right? This is the correct definition, I guess. T minus t0 is the finite interval, and there are n many of them, and so it is indeed epsilon. I can call it the epsilon, the infinitesimal one. How is it? Let me write the expression in here, then we'll go to the left corner to elaborate. What is this expression? It is x k. I'm coming from the smaller to the larger, so this should be, I'm sorry, for aesthetic purposes. As I said, we go in time to the right, an expression comes from right to left. Arabic alphabet direction, okay. K inverse, K inverse. We go that way. So what is this? Tk xk minus 1, tk minus 1, or xk e to the minus I over h bar h tk minus 1 xk minus 1. I have put back the time evolution operator and went back to the Schrödinger picture eigenvectors in position. So what is this? The crucial point, as is the case in all infinitesimal computations, is that I have written that as epsilon as an infinitesimal quantity, which simplifies the life tremendously. Why? Because then this operator can be written as 1 minus I over h bar epsilon h to leading order infinitesimal, retaining only first order terms. How nice. Then let's go back to here. Well, let me give this a name. It is the xk, I don't know, this is just to give a name. It may not be the best naming, but anyway. xk, and in the inside, in the middle, I have the 1 minus I over h bar epsilon h, Hamiltonian operator, x k inverse. Infinitesimal. So this is equal to xk minus 1, which is delta. I was planning to write a shorthand, but no. Well, that's explicitly what I have, right? That's fine. I can rewrite it in the following fashion. Using the famous representation of Dirac Delta. You realize where I am moving at now. This delta is written in this Dirac Delta in one of the famous representations. And what about this one? This one is p squared. Let me do it. Notice that I am doing it for this one-dimensional case for ease. Generalizing it to 3 dimensions is trivial. That capital P is the momentum operator squared plus v of x. What is it really? This one then becomes P acting on here, or to the left, perhaps it's more aesthetical. Hermitian, it can act to the right and to the left the same. So what does it give me when it acts to the left? It gives the following. 1 over 2m minus h bar squared minus h bar squared d squared dx k squared plus v of xk as I said, it can act to the left and to the right the same, times this comes out because this acts only to the left factor, so xk inverse. What is, then I can use the same representation of the Dirac delta, which is the normalization for this thing. And then move it in. Yeah, in the remaining few minutes, I have to take it to a proper place before stopping, because we'll continue on this line later. So what is it then? This k of kth interval is dpk divided by 2 pi h bar e to the I over h bar pk xk minus 1 minus I over h bar epsilon minus h bar squared over 2m d squared dxk squared plus v of xk times the same factor, because I'm re-representing now this as the Dirac delta. I am undoing and redoing it again. 2 pi h bar e to the I over h bar pk xk minus 1. Let's move this in. This moves in, and this derivative acts Well, this is a C number function. There's no danger in it. This derivative acts on the exponential, brings down what? I over h bar pk squared with a minus sign. H bar cancels, and it enters in here. Let me write this after it entered. After it entered in, it becomes dpk divided by 2 pi h bar pk squared divided by 2m plus v of xk. You may say, is it amazing? This is really amazing, isn't it? Times in front I over h bar epsilon. It's this thing there. What is this? Now I will denote this as h pk xk. This is a Hamiltonian, C number Hamiltonian, with the p as the pk C number and x as the xk C number. And you bring this in all together, and what do you have then? K of x, this infinitesimal, dpk 2 pi h bar 1, number 1 now, minus I over h bar epsilon h pk and xk times e to the I over h bar pk xk minus 1 Well, now you can resum. This is the infinitesimal version of the full expression. What if I go back to the full version? This is e to the minus I over h bar epsilon h pk xk. Keeping in mind that epsilon was infinitesimal, this was approximated as such. I have resummed, so the expression is back to its exact form, e to the I over h bar pk xk minus 1 minus epsilon h pk and xk. I have been able to find an integral representation of the generic infinitesimal transition amplitude in terms of the C numbers. Pk, xk, but notice that it's not that elegant yet, because there are these different appearances of the endpoints. I am referring to kth interval, which is rightmost point is xk, leftmost point is xk minus 1, but here in the h there is a v which is labeled by xk alone. Which one? Is it midpoint, left point, or right point? This is the, now we are at the threshold of all these most beautiful difficulties and subtleties of the path integral, but this is my starting point. Notice that it doesn't look Feynman's expression at all. It's not the Lagrangian. It has the, what is it? Legendre transformation from the configuration space to phase space. So it is really a phase space expression. And for special classes, I will reduce it to the configuration space, and I will recover Feynman's version. But we have to wait till we hit that point. Okay. So I think it's a good point to stop for the morning.